So now we have a constitutive equation for our Newtonian fluid. And that means we can express our stress state, the stress tensor Tij, in terms of the deformation of the fluid, in terms of the strain rate Sij. So the next step is to just plug this constitutive equation back into our Cauchy equation of motion. And just to recall, Cauchy equation of motion is the following. So if I substitute this in, number 1, substitute number 1 for Tij, I end up with the following equation. And this I can simplify a little bit and write as follows. Now I act with the x d by dx on the pressure term, and so the Kronecker delta contracts, and I'm just left with minus dp dxi plus the strain tensor term. For most cases, especially when temperature variations are small, we can say that the viscosity here is a constant. In that case, we can take mu out of the derivative and further simplify this last term here. That's the next thing we will do in a second. So let me copy this equation. So let's bring the derivative term into and act on these two individual terms here. And we'll see that d by dxj acting on the Kronecker delta again contracts to d by dxi. So I write this as now let's look at the first term in the parentheses here in detail. So this is a half d by dxj dui dxj plus duj dxi, which is a half d squared ui dxj dxj plus a half d by dxi duj dxj. And now remember that duj dxj is nothing else but sjj. So we can see that this term A will combine with this term up here, B. So let me write it out again. We'll have rho dui dt, and now we'll first include this term, which gets multiplied by 2 mu, so we're left with plus mu d2 ui dxj dxj, and then we have a half, we'll have this term a half d by dxi of sjj and minus a third of d by dxi skk. So those two terms combine to just give plus a third d by dxi duk dxk. And both of those terms are multiplied by the viscosity. So, in summary, this equation is our compressible Navier-Stokes equation. And in some ways, the whole course, the last 18 lectures, have been building us to get to this point, to derive this equation. So this describes the flow of a vector velocity field u for a given pressure P and density rho. And let's write it in vector form. Rho du dt equals rho g minus gradient of P plus mu times del squared u plus a third gradient of the divergence of the velocity. And if Sm skk, which is equivalent to the divergence of u, is 0, then we have an incompressible flow, and our incompressible Navier-Stokes equation is simply given as rho du dt so this is our incompressible Navier-Stokes equation. So let's count our unknowns. We have 5 unknowns really, namely 3 from u, rho, and p. And we have 3 equations. Navier-Stokes really represents 3 equations. And then we have mass conservation, so that gives us a 4th. So we can solve this system if rho is constant, for example. Then we only have 4 unknowns and 4 equations. Or if we relate P and rho. And often that relation between the pressure and the density requires a dependence on temperature. And so then we need a 5th equation, which comes from the conservation of energy. And this concludes our section on how to find the Navier-Stokes equation.